Welcome to Feza Gürsey Institute Higher Structure Seminar Talk. Today our speaker is Can Yaylalı from Technical University of Darmstadt, and he will talk on derived f-zips. We thank him for being our speaker. Can, please.
Okay, yeah. Thank you for giving me the opportunity to speak here. And today I want to talk about the topic of my PhD thesis, or what I did in my PhD thesis, namely a derived analog of, let's say, Hodge structures and positive characteristic, and to even maybe understand what I mean with Hodge structures and positive characteristic, and where this name f-zips comes from. I maybe start with explaining to you the motivation behind f-zips. Okay, so let f from x to s be a morphism of schemes in characteristic p greater 0. And we have two spectral sequences. And I will abbreviate these with SS because at some point it gets really annoying. On the Durham cohomology, sorry. Namely, we have the Hodge-de-Rham spectral sequence. This is an E1 spectral sequence. Yeah, okay, let's write the relative version. That goes from the Hodge cohomologies, I mean, these terms I call Hodge cohomologies, to the de Rham cohomology. And we have the conjugate spectral sequence. This is an E2 spectral sequence that goes from, well, the high direct image of the cohomologies of the de Rham complex to, again, the de Rham cohomology. Okay, and in particular, this implies that we have two filtrations on the de Rham cohomology, namely Hodge and conjugate filtration. Okay. Now, in contrary to characteristic 0, for example, we have an extra spectral sequence with an extra filtration. In characteristic 0, you would not have the conjugate spectral sequence. And okay, what is the nice thing about this? I mean, in characteristic 0, you have something, for example, you have complex conjugation, and you can try to get an extra structure on the de Rham cohomology with this. In this case, what you can do is the following. We don't have the complex conjugation. But what do we have is the Cartier isomorphism. Or inverse Cartier isomorphism. This goes from the ith object of the de Rham complex, but of the Frobenius pullback of our morphism to the cohomology of the Ram complex. Oh, sorry. With, okay, I have to push this forward via relative Frobenius. Maybe let's write this like this. Okay, this is an isomorphism of graded OX of P modules. And what is nice, I mean, what you can see more or less is that, well, the left-hand side of the hot spectral sequence, if we twist it by Frobenius, we get an isomorphism of the with the conjugate spectral sequence. And I can be more precise with this. Namely, if, and this property I call A, if these RPF, so the Hodge cohomologies, if these are finite locally free, then what we can do is we can pull back the Hodge cohomology. Okay, and because it's finite locally free, it commutes with arbitrary base change, and the relative Frobenius is affine, so you can show that this is nothing but the Frobenius base change of this. And so in particular with the Cartier isomorphism, what we can see is that this is nothing but the E1 page of of our the E2 page of the conjugate spectral sequence. So in particular, I mean, if we now take d bullet as being the conjugate filtration, or wrong bullet here, the bullet, and we take this to n-1, where we are n-I, where n is the Ram cohomology we are interested in, then what we get is an isomorphism between the Frobenius pullback of the Hodge cohomology in degree I with this di. With the graded pieces of this. Oh no, sorry. I'm completely lost here. Sorry. Okay, maybe I stick more to my notes. Sorry. I will come to that. Okay, sorry, I was a bit too fast because, okay, by this finite locally freeness, you have compatibility with base change, and then you get that the pullback of the E1 page of the Hall spectral sequence is isomorphic to the conjugate spectral sequence. And now if you go up, what you see is that if these things degenerate, then the graded pieces of the filtrations are precisely per definition this and this. So what you have is you have two filtrations, and if the spectral sequence degenerate, the graded pieces are isomorphic up to Frobenius twist. So, and this is what I call property B. We assume further that that the spectral sequences above degenerate. Okay, and what do we have? I mean, what is the data that we in the end get? We have a finite locally free OS module, namely we take the Ram cohomology. Okay, I mean, the spectral sequence degenerate, the graded pieces are finite locally free, so we have a finite, we have also a finite filtration, and in particular, these are finite locally free. We have a descending filtration. On the Ram cohomology, namely from the Hodge spectral sequence. we have an ascending filtration on the Derived cohomology coming from index shift and the conjugate filtration or conjugate spectral sequence. I mean, this is what I wanted to tell earlier, because what you see here is that we oh, here I made a little mistake. Sorry, this is P. Right, we have no, this is also wrong. This is also wrong. Oops, P Q. I mean, this is more or less what we want of the E1, E2 term of the spectral sequences up to index shift. So we have to shift the conjugate spectral sequence, the filtration of the conjugate spectral sequence, so it becomes an ascending one. And via this Cartier isomorphism, we have isomorphisms of the graded pieces of this ascending filtration, and here up to Frobenius twist with the graded pieces of the ascending filtration. So this is the Cartier, it comes from the Cartier isomorphism. Yeah, just to show you again, I mean, we assume that spectral sequence degenerate. So in particular, the graded pieces are given by these terms. And you see, okay, by the Cartier isomorphism, we get an isomorphism of the Frobenius pullback, but up to index shift. Okay, so we have to make the conjugate, the filtration on this side. We have to make an ascending one, and in the end we just get this structure, namely a finite locally free OS module, descending filtration on it coming from the hot spectral sequence, an ascending filtration coming from the index shift of the conjugate spectral sequence, and isomorphism of the graded pieces up to Frobenius coming from the Cartier isomorphism. So in particular, this endows the Derived cohomology, in this case where A and B hold, with an F-zip structure. And I mean, just because I didn't define it, let me now define it now. An F-zip over S is a tuple M C bullet D bullet phi bullet. I mean, more or less like above. We take a finite locally free OS module M. We take a descending filtration on M, which we call C bullet. And okay, you have to be careful. What we had was that the graded pieces of the conjugate of the hot spectral sequence were finite locally free. So the filtration is by finite locally free modules. And you have to be careful what filtration in this sense means, but it's just that each piece of the filtration is a direct summand of the next one. So in particular, if you start with a finite locally free module, each graded piece will be finite locally free, and each piece of the filtration will be finite locally free. Then, okay, what is missing? An ascending filtration on M, which we call the bullet, and isomorphisms of the Frobenius pullback of the graded piece of C with the graded piece of D. So this is precisely what we had in the Derived cohomology context, coming from the Hodgkin conjugate spectral sequence and Cartier isomorphism. Okay, and why is this interesting? I mean, basically the idea is always, okay, you have some complicated moduli space, and what you want to do is you want to linearize it. So you want to assign invariants and understand these invariants. And in the best case, these are just combinatorial data or linear algebra data. And in this case, for example, if you're over a field, and a finite locally free module is nothing but, okay, you can replace it by a free vector space of finite dimension. And then filtration and these isomorphisms are really just combinatorial data. And okay, one question you could have is, okay, I mean, this, when is this A and B satisfied? So smooth proper maps. Satisfying A plus B. Well, these are, for example, abelian schemes. K-free surfaces. Okay, and I think that's enough to be convinced, okay, that's you can do a lot with these structures. Namely, for example, what you can look at are Humour varieties of PEL type, and these are given by abelian schemes plus data. And what you can do is actually you take this abelian scheme and send it to the first de Rham-Kornmoldy. This is enough because for abelian schemes, the higher de Rham-Kornmoldys are already determined by the first one. And so if you have, for example, you take the spatial fiber of some model, some integral model of a Humour variety of PL type, and then you can look at the functor that sends, well, this abelian scheme plus data to H1 de Rham of A. This, in fact, because the right-hand side is just a combinatorial object, yields a stratification on the left-hand side. And the stratification is, for example, known as the equidal Ort stratification. And so you, also for K-free surfaces, you get refinements of known stratifications, because again, on the right-hand side, these F-subs, they also have you can describe stratifications via symmetric groups. And so this is really not a hard object. I mean, there's still a lot to do on it. It's not like it's not trivial to see what stratifications you get and how you what groups are involved and how you can, for example, attach a group structure on F-subs. But these are certainly nicer objects, or easier in quotation marks, than Humour varieties, for example. Okay. Questions so far, maybe? Okay. Yeah, I mean, this was done by let's say the above is by Moon and Vetorn. So this is nothing I did, especially F-subs. And okay, the results on abelian schemes and so on goes back to a lot of other people. But the question is, how do you get rid of these properties A and B? And this is more or less what I did in my PhD thesis. And the idea is not that difficult, because, I mean, sorry. You can ask yourself, okay, where do the spectral sequences come from? Okay, and as it turns out, you can do the following, and yeah, let me write it like this. Okay, we can attach a functor. Namely, what we do is we get a sequence of maps that are induced on truncations of the de Rham complex. Namely, I mean, we can truncate from the left stupidly. And what do we get is nothing but, I mean, just a sequence of complexes where, as a co-limit, we just get the de Rham complex itself. Okay, and you can go further, but this is just the identity. And you can also assign a functor like this. And with functor, I mean, yeah, just to be more, give an idea, I mean, for each n, you can assign the stupid nth truncation. And you can also do this for the canonical truncation, namely, if f, for example, is smooth relative dimension n, then we can truncate as follows. Okay, if f is smooth of relative dimension n, this thing here is nothing but the RAM complex, or quasi-isomorphic to, okay, no, it's in fact the RAM complex. And but okay, if we are, for example, in a local situation, in the co-limit, we will also get the RAM complex itself and here identities. And why am I writing this in a strange way? This will be apparent in a second. Namely, what we can do is we have these sequences of complexes, but we can also view them in the derived category. So what we can do is we can take RF lower star of this thing, where f of x is now a smooth proper scheme like before. Okay, and in particular, this Hodge and Conch, these can be seen as functors from the op to the derived category of S, or respectively Z to the derived category of S. Okay, and you may still ask, okay, why is this interesting? This will, again, I mean, just wait a few moments. We can relate these functors to spectral sequences directly. And how do we do that? Well, for example, if you look at these maps here, what is the co-kernel of such a map? Yeah, for the stupid truncation, this is rather easy. Yeah, you can stupidly truncate like this and get a sequence. And I mean, what is the co-kernel? This is easy. This is nothing but the ith term of the de Rham complex shifted by -1. Okay, and you can do the same thing with the canonical truncation. Okay, and let's call this theta. You get a co-kernel theta, which, okay, maybe this is not that interesting for you, but what you can show is, okay, this is quasi-isomorphic to the ith cohomology sheaf of the de Rham complex shifted by -1. So what we can do is we can just say, okay, let's get rid of these zeros, because I mean, we were going to work derived anyway, and apply RF lower star on here and also here. Okay, and so in particular in the derived category, these are distinguished triangles or co-fiber sequences. And now there's this really nice theorem of Lurie, and maybe this goes back to some other people, but I only seen Lurie's theorem. Namely, if we take a functor from Z to the derived category with f of I is equivalent to 0, where I is small enough, then we have that we get a spectral sequence like follows. Namely, we get, okay, I will do this cohomologically because Lurie does this in homotopy theoretical terms, but it does not matter anyway. We get that the the co-fiber determines the E1 page. And this converges to the H minus P, H minus Q of the co-limit of F. So I mean, if you look at now the above, okay, the co-fiber of the stupid truncation, this gives you the Hodge hypercohomology, and the co-fiber of the canonical truncation gives you the derived direct image of the cohomologies of the Durham complex. And okay, what is the co-limit of this thing here? Okay, if you look, I mean, if we go further, we get here the Durham complex, we get here the Durham complex, and I forgot to add here RF lower stars. And I mean, in particular, with this theorem, we get that this functor Hodge and this functor Con, they induce the Hodge and conjugate spectral sequence. So nice part is the following. If you look at all of this here above, in the spectral sequence case, we need a degeneracy to understand the graded pieces of the Hodge and for conjugate filtration. If we define co-fiber sequences as graded pieces, then this is clear, because in this case, we understand them completely. We don't need degeneracies to understand the graded pieces of filtrations on the cohomologies, but instead working with the derived objects, we automatically have knowledge about their graded pieces via the E1 page. So we don't need degeneracy to connect them in any way. Okay, what is still missing is, for example, this compatibility with base change. But there's a nice proposition, because we are smooth proper. And this is, you can find this in the Stacks project. If F from X to S is a smooth proper scheme, then, then the higher direct image of the nth piece of the Durham complex, or also the Durham hypercohomology, these are perfect. And the formation commutes with arbitrary base change. Okay, so in particular, what do we get in DS? We get that the derived pullback of this RF lower star of the Hodge hypercohomology is nothing but the Frobenius pull. I mean, just instead of pushing down, we can Frobenius pullback. Oh, sorry, this is okay. And in particular, we get that this is automatically via the Cartier isomorphism, isomorphic to RF lower star of the cohomology sheaves of the Durham complex. So the graded pieces, so this co-fiber sequences, the cones of both co-fiber sequences are automatically isomorphic in the derived world. And so in particular, we don't need this degeneracy of the spectral sequences to understand them. And this finite locally freeness we also don't need, because for smooth proper morphisms, this is more or less built in into the Durham cohomology. So just to recollect everything. So for X, for f from x to s, a smooth proper morphism, we have the following structure on the de Rham hypercohomology. Namely, what do we have? We have a functor that goes from z op to d of s, such that these each of the pieces is perfect. It's also bounded. We have a functor that we call conj from z to d of s, such that these are perfect. And we have equivalences of the graded pieces. Namely, I mean, now I can more or less also define it. This is nothing but the co-fiber, so the co-kernel in the derived sense. And this, with the Frobenius pullback, let me write it like this. To the graded pieces of the conjugate filtration. Okay, and I mean, what you now do is more or less transport this, like in the FZIP case, to another definition. But you have to be careful with some of the details. I mean, I will give you the definition of a derived FZIP now, and explain on the way why I made certain choices. A derived FZIP over S, this is nothing but a tuple. I mean, like before, two filtrations, then there's this omnius phi, and the equivalence is var phi. We have a bounded perfect filtration which is nothing but a functor from z op to d of s. And this means that the CI are perfect. Filtration really means that this is just a functor like this. And bounded, okay, at some point it should be 0, at some point it should just be isomorphic to the co-limit. Okay, then we have a bounded perfect filtration D bullet, which is now an ascending filtration. We have equivalences of the co-limits, and I will say a bit to this in a minute. This is co-limit in Z op, this is co-limit in Z, and we have equivalences phi bullet, namely of the Frobenius pullback, the derived Frobenius pullback, obviously, of the I've graded piece of C to the I've graded piece of D. Okay, and just to complete this as an example, we have, well, if f from x to s is smooth proper, then we can just take, like before, we take this Hodge filtration, we can take this conjugate filtration in the derived world. So these, just to show it again, we take these two. Okay, we take the identity of the co-limits, which is just RF lower star of the de Rham complex. And we take the equivalence induced by Cartier. Okay, and so in particular, without this assumption on degeneracy of the spectral sequence and finite local freeness, we have the same structure in the derived world. And again, this is not something you would not expect, because the spectral sequences are induced by filtrations in the derived category, and the E1 page is anyway given by cohomologies of the graded pieces in the derived world. So you don't need this degeneracy to understand what the graded pieces are. Okay, and this maybe, which seemed kind of ominous, is this these equivalences of the co-limits, but this is just, I mean, if you work with infinity categories, you can also think of group points, for example. If you take pullbacks of group points, there's always, you need to fix higher morphisms or higher equivalences. And here it's the same thing, because what you want to do is, if you want to understand derived f-subs or the infinity category of derived f-subs, you want to see it as a sub-infinity category of some larger category. And then you have to, I mean, basically it's just a product of certain infinity categories, obviously, because you take here an infinity category, here an infinity category, and you just want some conditionally graded pieces. So it will definitely be a pullback, but okay, then at this point you will automatically get that you need this to fix this data to understand it as a subcategory. Okay, and questions?
Actually, I have one question, but it is not about the derived f-zip, but f-zips.
Yeah.
It may be a very stupid question, but for example, when one applies this f-zip theory to the theory of Shimura varieties, can one use it to do point counting on Shimura varieties? Can one apply f-zip theory to point counting?
Ooh, okay, I'm honest. I don't know. This would be probably a good question for Thorsten, but I certainly don't know.
Because you said that f-zips are simpler to study than Shimura varieties and encodes data of Shimura varieties.
I mean, in the end, what you do is you want to understand, I mean, isomorphism classes for f-zips are rather simple. And what you do is you stratify these objects. These have nice stratifications, and then you try to apply this via this period map to Shimura varieties. So you can certainly get information about the geometry, but about the points, I don't know, to be honest, because then it gets more difficult. Because I mean, okay, f-zips seem simple, but definitely only there as a combinatorial object, and then I need isomorphism class, and then I don't know if you can really do some point counting. But okay, I'm also not an expert on f-zips. I'm an expert on, I mean, I just studied derived f-zips. So this is unfortunately not really a question I can answer.
Oh no, it is just
that well, but I can, to be honest, I can ask Thorsten.
Yeah.
And I can write you a mail. This is definitely
Perfect.
possible.
Yeah. Thank you.
Okay. So okay, what is the next part? I mean, okay, we had f-zips, and you try to do the same thing with the RAM hypercohomology. This leads to derived f-zips. Now the problem is, to understand something like a period map, you need to understand geometry. And okay, what do you need for geometry? You need two things. Namely, you need descent, because I mean, a geometric object should be something that you can glue locally if everything intersects nicely. And this is definitely possible here in the infinity categorical sense, because okay, first, I mean, this is like the first obstruction. First, work infinity categorically. Because I mean, what we have is, for example, and this can also be found in Lurie's spectral algebraic geometry, the functor that sends S to the derived infinity category of S. This is an FPQC sheaf, even hypersheaf, but okay. Okay, so I mean, this obstruction is more or less gone because the derived F-zips are nothing but objects in the derived category plus morphisms plus equivalences. Okay, everything glues nicely because the objects satisfy descent. Okay, and in the next step, okay, what you would like to have is also like coverings of something. So you would like to have a theory of algebraic stacks in this case. And what we need is a replacement of algebraic stacks in the infinity world, because I mean, now we have sheaves, we can glue things nicely, but we would also like to understand, okay, we can cover it by affines and then reduce everything we want to affine schemes, because affine schemes are nice. Okay, and what you do is the following, and this is a lengthy definition, but so what you take is you take an étale sheaf with of infinity group points. This is called -1 geometric. If okay, it is affine, and same for morphisms. This is the first step. Okay, then what you need is, this is going to be an inductive definition. So X is called this is called n-geometric if there exists a smooth atlas and I will say what smooth means in a bit, such that, okay, these morphisms spec AI to X, these are n-1 geometric, and the diagonal is n-1 geometric. Okay, and so when is a morphism called smooth? Sorry, a morphism is called n-geometric if for all affine points the base change, if this is n-1 geometric. Okay, and I didn't say something too smooth, but okay, if for affine schemes, you know what smooth is, you do know what affine, for affine morphisms, you know what smooth is, and now you take more or less this definition, which is defined inductively, and apply it to smooth. And I mean, this is not really definition, I would say, where you just see it and think, okay, yeah, it's clear. What you should maybe imagine, and this is what I imagine, smooth locally, it just gets more and more affine. Because I mean, if something's n-geometric, then you can cover it by something which is which is n-1 geometric, and then you go further and further and further, and at some point you are -1 geometric, which just means affine. And not only that, I mean, why should this be interesting? Because if you have, if x is an n minus, if x is an n geometric stack, and A is just a commutative ring, then x of A is n plus 1 truncated. Because this theory of n geometric stacks was first developed by Simpson, and the question was, okay, now I have stacks of groupoids. This is kind of nice, but what if I want to have higher groupoids? And what is the right notion of a cover? It turns out that this gives you the right notion of a cover in a certain sense. So you just need inductively, by base change, more and more covers, and by getting more and more affine, you can show, okay, it's actually not an infinity groupoid anymore, but it's actually truncated. And okay, with this, for example, we can define properties like smooth, flat, locally affine presentation, open immersion, closed immersion, and so on. So it just needs to be smooth, local, on target and source, and then you can just define it like always. Namely, you for every point you have to take the base change, and then you have to find a cover which is already smooth, and then this cover has to have this property because you can reduce everything to affine things. And an example which is really more or less a major example for me, this is by Thon-Vaquier in the simplistic commutative ring case, in the model categorical case. Then Antje-Gebner gave a proof in the spectral case, and then okay, I did everything in the infinity category of animated rings, so more or less doing the same stuff as they did. This is not that special. The functor perf AB that sends a ring to its largest infinity groupoid of perfect complexes with Tor amplitude in AB. This is B minus A plus 1 geometric. Okay. And just because, I mean, it should be a short talk, what is the idea of this? So how can you prove this? If you take A and B to be 0, what you have are perfect complexes of Tor amplitude in 0. This is nothing but a vector bundle concentrated into degree 0. So the stack is nothing but the stack of vector bundles. This is certainly an algebraic stack, so it's one geometric. Okay, and because everything is defined inductively, the idea is, okay, use also to prove this inductively. Then you show any perfect complex of Tor amplitude AB. This sits in a distinguished triangle of fiber sequence of a projective module and something with a smaller Tor amplitude. And if you have this, okay, then you can use vector bundles and perfect complex with smaller Tor amplitude to cover this, and inductively this shows you that this is geometric. Okay, and why is this interesting? I mean, derived F-zips, these are nothing but perfect complexes plus morphisms of perfect complexes, plus equivalences of perfect complexes. And so what you get in the end is, if you take a finite set, so if you fix the graded, we want to fix where the graded pieces can even appear. We want to also fix the tau amplitude of the perfect complexes appearing. Then you can do more or less the same thing, namely you'd send R to the largest infinity group point of derived F-zips. Over R, such that the graded piece of C is equal to 0 for I not in S, plus the graded pieces of these have tau amplitude in AB. Okay, and then you get the same result as before, namely this is a B minus A plus 1 geometric stack. Okay, because I mean, you just glue everything together. You have perfect complexes and you glue morphisms together. You have to show that morphisms are geometric. This is not that hard to show, but okay, it is definitely true. And equivalences are perfect because I mean, what you have to show is when is a morphism of perfect complex and equivalence? Well, the cone has to vanish. Okay, and the vanishing locus of the cone is just open, so it is also geometric. And then this is everything you need. Okay, and are there questions right now up until this point? Yeah, I don't know why, but apparently, I mean, you can see it on the screen, my iPad time froze, so I did not know what time it was. Okay, let me say the following, just to wrap this up. I mean, you could ask yourself, okay, why? I mean, am I even interested in this? Because I mean, I have abelian scheme, I have Shimura varieties, and I have F-zip. So why look at something which is even more difficult? There are surfaces, and I can give explicit examples that have non-degenerate Hot spectral sequence. Namely, and one example which I worked with are Enric surfaces. These are okay. I mean, I can give you the definition, but let's say one can explicitly calculate the Hodge numbers and the de Rham cohomology, dimension of the de Rham cohomology, and it's not hard to see that in characteristic 2, there are 3 types of Enric surfaces. Classified by the torsion part of the Picard group. Namely, I mean, one can show that the Picard group is either alpha 2, mu 2, or z mod 2. And in this case, the Hodge spectral sequence does not degenerate. Because I think the de Rham cohomology has something like dimension 10, and the dimension of the Hodge numbers are, if you add everything up, you get something like 12. Okay, and then you can try to do the same thing. Namely, you look at the period map M moduli of Hendrik surfaces in characteristic 2. Polarization.
John, I think the internet, there is some interruption in your internet, I think.